This question is titled, Are you tuple on the list? And in this question, we're going to talk about the difference between the list and the tuple. We'll talk about what they mean, because that's the most important question in Python. What does it all really mean? And we'll talk about the relationship between hashability and immutability. There are a couple of things that we won't talk about. We won't talk about why collections.nameTuple is so useful, how it comes up in practice, and how it relates to data class.dataClass. We won't talk about the difference between the tuple modeling of an object and the object modeling of an object. We won't talk about the difference between identity and equivalence. We won't talk about the difference between the double equals and the is operators. And we probably won't have time to talk about whether it's tuple or tuple, because it turns out it's actually two-ple. So let us take a look at our problem that has a bug in it. Here we have some code. Can you spot the bug? If you said that lists are not hashable, you spotted one of the bugs. If you said that I forgot to do a dot items, sorry, let's go up here. I forgot to do a dot items here, you spotted the other bug. There were, in fact, two bugs in this. I didn't do a dot items when I was iterating over this dictionary, but apropos with this particular question, I had the keys of the dictionary be a list and not a tuple. And this is oftentimes where people first interact with this tuple type. They see it pop up and they're like, oh yeah, that's when I need to have something that's kind of like a list, but I put it into a dictionary, and the dictionary has to be something that the keys of the dictionary have to be hashable, and that corresponds with immutability, and that's why the tuple is interesting. But here's what I'm going to tell you. The least interesting thing about the tuple is that it's immutable. It is an interesting thing. Look, if I'm at a party and I have my drink, and I'm like, so tell me about yourself, tuple. And the tuple says, I'm immutable. That's kind of like saying, I work downtown at the bank. Yes, it's important. It's a big part of your life. But tell me what you do for a hobby instead. Tell me about yourself. Tell me what you stand for. Tell me what you mean. Don't just tell me that you're immutable. What you mean is the most important thing when we try and decide what of these built-in types do we need to use to solve our problem. Fundamentally, the Python list represents a collection of linearly ordered data. It's a bunch of data elements that are all largely similar that we loop over in some fashion, whereas the tuple represents an ordered grouping of fields. And you can see these are distinct, but you might not see the distinction quite yet. When we work with the list, mechanically, it is mutable and it is not hashable. When we work with a tuple, it is mechanically immutable and it is hashable. And it is an important detail. It does make a difference, but it's the least important detail. As an aside, before I tell you a little bit about the tuple versus list, let us visit this mutability versus hashability, because this is something that I see people say that is wrong all the time, that immutability implies hashability, that hashability implies immutability, and that is 100% dead wrong. And I'll prove it to you. The slice object in the Python built-ins is immutable. You cannot change it when you create it. But it is not hashable. Immutability does not imply hashability. This is immutable, but it's not hashable. Now, there's a reason for that, and you might say that it's not the best reason in the world, but there is a reason for it. But just because it's immutable doesn't mean it's hashable. And on the other end, this is a small version of a very common problem. When doing the aforementioned project on mesh optical network planification, we had graphs because we were planning out mesh optical networks. So you had graphs of the different cities and how the different cities connected, and you'd plan out where the transceivers were, where the amplifiers were. Each one of the cities or each one of the nodes might be an amplifier, and you're connecting how all the fiber optic cables are connected. Those amplifiers might be mutable objects, because you have parameters on them and you want to tune them with your against things like your power sweep to see what the best parameters are. You might model the node as a data class that's mutable. You might put it into a network X digraph that uses dictionaries under the covers, and so the nodes have to be hashable. Node here is mutable and it's hashable, saying that hashability does not imply immutability. There is a relationship, but it is a coincidence. There's a correlation between them, but maybe not a causation. Here's the case. Hashability requires immutability if and only if you want what you might call disintermediated random access. In other words, you basically have two ways to compute the hash of something, either by its equivalence, by the data that it contains, or by its identity, the exact object. If you hash by equivalence, there is a risk that you cannot retrieve an object because you mutated it, and you can no longer retrieve it by its equivalence, by its contained value, if you put it into a dictionary as a key. If you hash by identity and you lose access to the exact original object and you try and recreate a totally equivalent object, you have the risk of losing something because you can't reconstruct that original object exactly. You can only reconstruct something that's equivalent to it. And if you're hashing by identity, the only way to retrieve the corresponding value for a key is to get the exact original object. And so this suggests to us that for something that's mutable, you can neither hash by equivalence nor by identity. Mutability implies non-hashability. But the additional qualification is this. As long as we're not looking to retrieve one specific key value pairing, which is what I call random access, direct access, arbitrary access, and we don't care about retrieving this using the exact key access, the key object rather, what I call disintermediated access, it doesn't actually matter if it's mutable or immutable. If we retrieve the entire content of the mapping with some sort of non-random access, sequential access, or if we use a secondary structure or object that sits between the key and the structure, an intermediated access, it is completely and 100% okay for a mutable object to be hashable, and you hash it by its identity. Here is sequential access. You loop over the dictionary and ask what keys it contains. You can't lose something. The dictionary knows what it contains, and it just tells you everything. This is not random access. This isn't, give me just this one over here. This is, give me everything. And if you have a subordinate structure in between, like a mapping of the data to the node, you can use this as a go-between to do intermediate access. And this is how you solve the problem, like our aforementioned mesh optical network planification network X digraph, where each one of the nodes happens to be a mutable object referring to a particular amplifier. But back to our list versus tuple topic. In general, list versus tuple is not mutable versus immutable. It is the least important or the least interesting distinction. It is collection versus record. Here, I have a bunch of cities. I have a collection of cities. I wrote some code to loop over the cities and to uppercase them. This code is valid if there's one city, if there's 10 cities, if there's no cities. If I clear out this structure, completely valid code. It still runs, it just doesn't do anything. If I append another city to it, completely valid code. Here, let's append Madrid. Still just as valid. What we can see is that lists are a way for me to say, I don't have one of the thing, I have a bunch of them, and I'm going to repeatedly do the same operation to them. That's a collection. Whereas a tuple is some sort of structured data. Here, Paris and France are not equivalent. One is a city and one is a country. But I can store them together in the same object, in the same tuple, as two fields of a single conceptual entity, as a location. And I can unpack it to get the city and the country out. Or I can combine these two, and I can have a list of locations where each one of these is a record containing the city and the country. And I can use both looping syntax and unpacking syntax. Fundamentally, when you're working with your data, you should ask yourself, are these three fields that refer to one entity, or are these multiple entities? Am I going to do the same thing to every single one of these entities? Or am I going to take each one of the fields, and one of the fields means the city, one of the fields means the country. I print the city up here on the postcard. I print the country down here on the postcard. So what do we do about this? Whenever we are using the built-in types in Python and we see a need to store some sort of ordered data, that's not a mapping, that's not a dictionary, we should ask ourselves some key questions to determine whether or not we want to use a list or a tuple. This is what I call modeling the data. The data exists in the real world in some way that somebody describes it, and you model it using the tools of your programming language, your list and your tuple and your other built-in types. If your data is a collection, that is a bunch of elements that are conceptually similar, so that you can do the same thing to each one of them. You loop over each one, you do the same thing, it's loosely homogeneous, that's a list. If the code using this data is valid if there's one element or two elements or a million elements or no elements, and it's valid to treat it in a mutable fashion, appending to it and clearing from it before you do anything with that data, then it's probably a list. If the order of the elements reflect the order in which you process them, the order in which you handle them, then it's probably a list. If your data refers to one conceptual entity, a grouping of fields, if there are a fixed number of fields, there's only city and country. If you want to unpack it and do something different to the different elements, you print the city up here, but you use the country in order to figure out what the postage rate is or what the name of the postal system is. It's heterogeneous. If it's valid, if the fields only have a specific order, because Paris, Texas, and Texas, Paris, they're different. Texas, Paris, that might be a street somewhere in, I doubt it, but it might be a street somewhere in France, whereas Paris, Texas is clearly a city somewhere deep in the heart of Texas. Well, you probably want a tuple for that. Now, there are some cases where these overlap. In some cases, you really want to use a list, but you're constrained by the programming language, you're constrained by Python to use an immutable or hashable type. Although your custom types that are mutable can be made hashable, you can't make a list hashable. You can't add that behavior to it. It's fixed in place as one of the built-in types. And in those cases, you may sometimes find that you use a tuple where you would otherwise use a list if you needed something that happens to be mutable or hashable, for example, in the keys of a dictionary. Let us go to our next question. Our next question is titled, "Would you please zip it?" And in this question, we'll talk about looping, iteration, and iteration helpers. We will talk about what zip and enumerate are. We'll talk about what iteration helpers are, what problem they solve, and we'll talk about what it means to write more readable code. We will not, unfortunately, have an opportunity to talk about what the itertools module is, why it's so incredibly useful, why it's one of my top 10 imports in any program that I write, whether it's NumPy code or Pandas code that I'm using. I always end up having the itertools module somewhere there. We won't talk about comprehension syntaxes, what generator expressions are, or what a generator is, but we do have additional videos that talk about all the syntax that you didn't learn in school in Python. That includes things like comprehension syntax, which we will provide to you. If you're interested, just reach out to us. We won't have an opportunity to talk about complex iteration helpers and how you would go about writing them and how you can use these tools as building blocks and some of the process for how you write them. And we won't talk about how you deal with modalities, when code should be kept ad hoc, when it should be superficial, when it should stay visibly ad hoc. Instead, why don't we take a look at this code and ask ourselves, can you spot the bug? And if you said there's no bug in the code, you're right. The code, as written right now, has no bug. But if you said there's a bug if one of these three structures changes, here I'm looping over each city, each population, and each demonym in order to print out London has a population of 8 million Londoners. Berlin has a population of 3 million Berliners, or I guess if I were to say it like JFK, Berliners. Here, there's no bug, except if one of these happened to be longer than the other, this would break. So if I had Amsterdam here, well, I actually need to loop over the range from the smallest of them to the largest of them. Otherwise, if I were to add Amsterdam up here, I'm basing this off of the length of the number of cities, but I don't have corresponding elements in my population. And so, there we go, Amsterdam. You'll see I'll get this index error list out of range. So if you got that, I think you get a bonus point. Here, there's no bug. I do the minimum of the lengths of these, and so I make sure to match up the smallest of the lengths against the other structures, and I pull things out. But if you said this is a prime use for zip, you shouldn't have had this problem in the first place, didn't use zip, if that was a bug you spotted, you're 100% right. That's worth the most points because this is a canonical example for where I want to use this built-in called zip. Let's take a look at another problem. Here I have some data that I'm going to pretend exists in a CSV file. And I want to take this data, and I only care about the column that has the city and the population. And I want to have a mapping that I build with each city and each population. I'm going to run this code, and it's going to be buggy. Can you spot the bug? If you spotted the bug and you said it was a value error because it's interpreting the header line as a line of data, and it's saying that, oh, I can't turn the word population into an integer, you got it right. The bug here is I didn't skip the header line. I'm supposed to skip the header line. I'm supposed to just see the 3 data lines, not the header line, and I forgot to do that. And there's many ways I could go about doing that. Let's talk about one way. Here's one possible way I could have skipped the header line. But this is still buggy. Can you spot the bug? Here, in this example, I capture the line number, and I say if I'm on line number 0, skip the loop. And that way I skip over the header line. And so I don't have this value error when I'm trying to turn the word population into an integer. I just look at London, Paris, or Berlin, except when I look at my output, there's no output here because I forgot to increment the line number in that first step. So I always had a line number of 0. So this is buggy code. And if this was really hard to spot the bug on, you might think, is there a way for me to make my code better by making the bugs harder to represent? Rather than spotting the bugs and training myself to spot the bugs, and rather than trying to train myself to avoid the bugs, can I make use of better tools so that the bug couldn't even exist in the first place? This is a canonical use of enumerate. And here, you can see there is no bug. I should actually remove this because there is no bug. This is a canonical use of enumerate. Instead of updating the line number, we just enumerate these lines. And I guess the one thing that you might kind of say is a bug is line numbers start counting from 1, not from 0. So maybe that's a little bit better. But here you go, the working program. What does this all tell us? When you look at the built-in functions in Python, not the things in the standard library, the stuff you have to import, the stuff that's already there ready for you to use, you'll see many of them are what we would call iteration helpers. They're things which help us in for loops to iterate over data. Things like sorted, which sorts one data set and then gives you the ability to loop over the contents of that data set in sorted order. Reversed, which gives you an ordered data set and allows you to look at the elements of that data set in reverse order. Zip, which allows you to take 2 data sets and pair them up. And it ends at the shorter of them, just like the zipper on your jacket ends at the shorter end of your jacket. That's what zip does. Enumerate allows you to take one data set and supplement it with, this is the first item marked as 0, this is the next item marked as 1, or from any starting point. This is item 1, line number 2, line number 3, line number 4. Map, which takes a function and lets you loop over the data in your data set, but applies that function to each element. Or filter, which allows you to take a data set and only loop over the elements of that data set which match some particular condition, some particular predicate. Map and filter are kind of outside of what we'll talk about to a large degree because map and filter are much less popular in Python these days when we have more ready use of generated expressions and comprehension syntax. But sorted, reversed, zip, enumerate come up all the time in my work, and they should come up all the time in your work. But beyond just memorizing these 4 tools, I want to talk about what these tools represent. What do they really mean? Iteration helpers are about moving complexity into the header of your for loop. They're about improving readability by really thinking, how do people read code? They skim it. Nobody gets a 50,000 line file and reads through every character of it. Who has time in their life to do that? So what are you going to do? You're going to skim it. You're going to look for the broad strokes. You're going to see what functions are defined, what classes are defined, how many files are there, what are the names of the files. Within one particular file, you're going to see a bunch of loops. You're going to read through the body of those loops? No. You're going to look at the heading of those loops. And you're going to look at the heading and say, oh, you're looping over each country. Oh, you're looping over each city and state in my list of states. You're looking over each population and each city. Oh, that gives me a sense of what you're trying to do. And then you look at the loop body. In the previous example, the line number, all the administrative mechanics of updating that line number were in the body of the loop. They weren't in the header of the loop. Meaning, looking at just the header of the loop, you couldn't get a sense for what is this loop actually operating on? When does this loop start looking at data? When does it stop looking at data? Which of the data elements does it look at? And what is it actually working with? Iteration helpers move that complexity into the header, so the header tells you, I'm looking at exactly the piece of data, subject to this transformation, subject to this filtering, with this additional supplemented information. And in fact, all of the built-in iteration helpers follow a particular pattern. They either transform the data, that's what map does, they reorder the data, that's what sorted and reverse do, they filter the data, that's what filter does, they supplement the data with additional information by joining two data sets together or by adding a counter to one of these data sets. That's what enumerate and zip do. You can write your own iteration helpers, and you should. And so, another way for me to write the CSV processing is to write my own iteration helper using generator expressions, which is a small little detail, but to write something that says, given some data set, mark which lines of that data set are the header lines. And so now in my loop, you can see, if I were to hide this code and I would look, okay, what does this loop do? It goes through my CSV data using my standard library CSV reader, identifying which of them are header lines, and it gives me whether it's the header line, what the city is, what the population is, and I didn't care what that third value is. So I'm going to do something with the city and the population and whether it's a header line or not. That's a really good summary of what this loop does. I don't need to read further in the body. But if I happen to, I could say, oh, if it's a header line, you skip it completely. That makes a lot of sense. Otherwise, you put it into your dictionary and you make sure that the population is a number. You can see here that what we're doing is we're moving that complexity into that header because that's how people read your code. They skim it and they look for the point. You want that bottom line up front, not hidden amongst all the details deep in the bowels of your code. Another way you could have written this is you could have written an iteration helper using a generator called skip headers. And this does the same thing as before. And when you read this code, you may say, oh, I actually kind of like this a little bit better. This says, for each city and population, and I'm going to throw away the last one, I don't care about it, in my data, using the CSV reader, skipping the header lines. And you might say, okay, that makes a lot of sense. I really like that. I'm going to look at the city and the population, not the header line, from my CSV data. I'm going to do something with it. What am I going to do with it? I'm going to convert each one of the population to integer and store it in a dictionary. You can see we have dramatically improved readability with very little change to our code just by writing an iteration helper. We should be writing iteration helpers all the time. They are a humongous way to improve the readability and the understandability of our code. Because fundamentally, what do we do about all of this? Whenever you're writing loops, which is probably all the time in your code, you have to remember every line of code is a sentence. People read your code kind of like a narrative. If you are writing code in assembly, then they're going to see an enormous amount of mechanics just to get that to work in the first place. If it's C, think about how hard it is to do simple things in C. You got to have the malloc, you got to have the free, you got to have the pointer dereferences, you can do the address of. That's the nature of those tools. And that's what you're buying into when you're using those tools. You say, I am so micro-focused on the steps that are taken, the mechanical procedure, that I'm going to use assembly, I'm going to use C. In Python, you say, you know what? I'm more focused on the human process of collaboration. I don't need to go over each individual microscopic mechanical step of what's happening. I need to give somebody the big picture because I need to collaborate with people who are semi-technical or who are semi-invested in my work. Semi-technical meaning they know kind of code, but they don't code every day. Like a manager who used to code but now manages projects. Or somebody who is semi-invested in your project. A hotshot coder who doesn't have time to read 10,000 lines of your code, but could skim it and tell you, does this seem right or wrong? Do you really want them to get trapped up in the nitty-gritty mechanics, or do they want to see the big picture? Do you want them to read through your code and to see, okay, on this line, they're trying to do some loop, some repeated operation on the city and the population. On this line, they're working on it. On this line, when they're doing that looping over the city and the population, they're skipping the headers. What does that do? Oh, actually, I don't care how that works. I just care that it's there in the first place. And you could think that the distinction between this and this is something that somebody who is semi-technical or semi-invested in your problem could give you feedback on without having to know how skip headers works, unless they were concerned about the mechanics of that, but largely they can give you feedback independent of the mechanics of this. Meaning, they could say, oh, no, for this file you don't skip the headers. It doesn't have headers. But they don't have to know exactly how skip headers works. This is how we get readability in Python, and this is why we're using Python in the first place, to express our human intentionality, what we're trying to accomplish, minimizing our mechanics. So what we do is we think about that. Every time we write a code, we say, when somebody reads this, is this a sentence describing what it is we're trying to accomplish and minimizing the amount of noise of the mechanical steps that we do to take to implement that. In other words, we focus on the why and the what, maybe a little bit more than the how. The second thing that we might do is we want to use the built-in iteration helpers. We want to use enumerate and zip. We want to use them whenever we see them. We never want to do that, for x in range, len, whatever, and then try and figure out how to match things up. We want to try to avoid that and use enumerate and zip and use them all throughout our code because they will add so much readability. They are so helpful. And when we are ready to use generators, generate expression, comprehension syntax, or the iter tools module, we want to write our own iteration helpers like the aforementioned headers or skip headers. These are things that will increase our readability. And so many of you have seen the 4 very common iteration helpers that I write as building blocks from the iter tools module. It comes up all the time in my talks. There's NYs, NYs longest, first, and last. These are very dense. And I never have an expectation that anybody can write them off the top of their head, that anybody can immediately read them or even spot if there's a bug in them. But what I anticipate is if I use them, people can make sense of what the code is doing independent of the mechanics of how it goes about doing that. If my data is the letters A, B, C, D, and F, and I loop over them, I should get A, B, C, D, E, and F. If I loop over NYs, NYs means not pairwise or 3Ys or 4Ys, but NYs, any paired grouping of these. If I loop over that, I get A, B, B, C, C, D, D, E, E, F. I get windows of some size of my data. And there we go. Oh, and here I should say this has 3 values, so I should do the next X as well. You can see the nice thing about NYs is this gives me a view into the future, a view into the past. So anytime I'm working with some view of the future, a view of the past of my data, an NYs-like structure is a really nice way to encode that in one simple line of code. And you can see, what does this code do? It looks at the current value, the value that's coming up, and the previous value, and it does something with them. If I use first, I can identify which are the first values I'm looking at and which are the last values I'm looking at. And so you can think, oh, it's important when you're processing this structure, this ordered structure, to do something special for the first couple of values. Or if I use last, it's important for me to do something with the last couple of values. Or if I use first, last, and NYs. This line tells me I'm looking at my data in pairs. It's important to me which one's the first value and which one's the last value. And I want to do something with knowledge that I'm at the head of the list or at the tail of the list. Or if I'm in the middle, do something with the previous value and the current value. And when you zoom in, you can see, oh, that's actually kind of looking nice because, it's going to have something that says, if I'm at the first, do that action. If I'm at the last, do that action. Otherwise, do some other action. Here you can see what we're aiming for is human readability by hiding complexity. This is a unique thing about Python, this focus on readability and ergonomics. And Python says the underlying mechanics are not as important as human expressivity. That is not the perspective that every language takes, and it's not the perspective that every programming language should take. But it is the perspective that Python takes, and I think you can see how, if you're okay with using Python, you should be okay with doing this. If you're using Python for that intentionality in the first place, for expressing that intentionality in the first place, you can see that these iteration helpers are a big, big help. Our last question is titled, Can I Just Set It and Forget It? And in this question, we will talk about the set and the frozen set. We will answer what the set is and the frozen set and what they mean. We'll answer where they come up in real, everyday programs. But unfortunately, we will not be able to talk about the relationship between the set type and the collections.counter and the pandas.series, even though that is a very interesting thing to talk about. They have some really interesting relationships, and there are some very important caveats on how you would model one using the other. We also won't talk about what happens when you need some of the requirements of the set unique elements, or the mathematical operations, and some of the requirements of the other types, the list, human ordering. So unfortunately, we won't have a chance to talk about that. Instead, let's take a look at this data. We are performing a reconciliation report. We are performing a comparison. We're comparing some values that we captured before and some values that we captured after. And our report is going to say A was 3 before, 9 after, and the delta was 6. B was 4 before, 4 after, and the delta was 0. C was 5 before and then something after, and that's what the delta is, and the same thing with D. Can you spot the bug? If you said we didn't take into account that something could be in the before but not in the after, and our lookups here may fail, you got it. That's going to happen. Think about a reconciliation report. If you're comparing two things over a period of time, is it always the same entities? If you're looking at some data in January and some data from June, some of those entities might be common between January and June. Some of those entities might have been decommissioned, might have been commissioned, may no longer be relevant, may be irrelevant. Who knows? So we have to take that into account. And if you said, maybe the solution would be, we check to see if the values in the after set, we go over everything in the before set, and we check to see if the values in the after set, that's maybe slightly more correct than we had before, but we didn't get a row for C or D, and we probably want to know that C and D are there. We want to know that C was there, but only in the before, and no longer exists in the after. We want to know that D was there in the after, but wasn't there in the before. And so if you said, we'll do something like this, okay, we see if it's in the after, and if it's not, we print out a dash, and otherwise we go through everything in the after, and we see if it's in the before and print out a dash. I'll tell you what, the output looks a lot better. It's got all 4 of the entities that I saw, and it tells me whether it was there in the before, whether it was there in the after, and if it was there in the before and the after, it tells me what the delta is. But I could not eyeball this code and tell you if it were correct or not. And there's this weird asymmetry here where this has an if-else and this only has an if. And if I put an if-else into that, I'd see some duplication of rows. I don't know if I like this. If you thought that the problem here is that I didn't use a set type, you're absolutely right, because the better way for me to work on this, the better way for me to work with this data is to take the set of all the elements in the before, the set of all the elements in the after, and to compute the intersection. Give me all the information for what was in common. Then take the set of what's in the before and the set of what's in the after, and look at what's in the before but wasn't in the after and print out those lines, and do the same vice versa, and I get the same output that I had before, but I can now eyeball this code, and I can eyeball this code just from the headings, do everything with the ones in common, do everything the ones unique to the before, do everything with the ones unique to the after. And I don't have that weird asymmetry. What does this tell us? In the Python built-ins, there is the set type, and it represents a mathematical set, the set that you learned about in your high school math class. But that doesn't mean that this is only a tool for mathematicians. This means that it is a structure which the elements are unique. Either an element is in the set or not. That's the only question you can ask, and there is no human ordering for these. You cannot predict what the order of the set is. You cannot use it as part of your problem because you don't care. A set of A, B, and C is the same for your purposes to the set of B, A, and C. So it's the same as C, A, and B. You don't care what the ordering is. That's not an important characteristic. And you choose to use this set because it implements these mathematical operations which have common sense meaning. A and B is the intersection, the set intersection. That means give me everything that was in common. For the before and the after, give me all the things that appeared in both. If you had a data set of data that I created and a data set of data that somebody else created, give me all the data elements that we both saw in our analysis. A pipe B is A union B. It says give me all the unique elements. So if I have a data set and you have a data set and we take the union, we get every unique element that we saw, not double counting anything. And that might be useful for our analysis to see, what was anything that anybody saw in the field? If we do the difference, this means, what were the things that you saw but I didn't see? Or the things that I saw but you didn't see? It's the set difference. Give me all the elements in A that are not in B. The most interesting of all of these, in my experience, outside of the intersection and the union, is the symmetric difference, and it comes up all the time in reconciliation code that I write. The symmetric difference is, give me all the elements that were uniquely in A exclusive or B. Give me everything that was in the before but not in the after. Give me everything that was in the after but not in the before. And you can think of that as the inverse of the intersection. The intersection is what's in common. The symmetric difference is what's not in common. And if I were doing a reconciliation report, one thing that I might want to do is I might want to say, here's what was in common and here's what the deltas were. And here's all the elements that just dropped out of the analysis because they weren't in the after or they weren't in the before. Oh, that's actually kind of useful. And that doesn't really require that I be a mathematician. It just requires that I want to work with data sets and find commonalities and differences in the keys of those data sets. Now, the set type does have a restriction. The elements must be hashable. And unfortunately, what that means is here, this thing is what you and I might call a set of sets. It makes a lot of sense. Set of sets. I'm pretty sure I heard that when I was sleeping through math class in high school. But this is not possible because the set type in Python is not hashable. The set type in Python is mutable. And even though we say that mutability and hashability, they go hand in hand, but they're not tied to each other. They're not completely, they don't imply each other. It's not an if or only if relationship. Well, the set type is mutable. The set type is not hashable. You cannot have a set of sets in Python. There is another type that you may come into contact with, the frozen set. The frozen set is just a set if you happen to be a penguin. Or if you happen to want a set that is immutable, a set that is hashable. You can have sets of frozen sets in Python, but you can't have sets of sets. That's what the frozen set's all about. Now, let's close this here. And you can see we have our unhashable, and there we go. Now, one other bug that you might run into. Here I have a dictionary mapping some number to its square. -3, its square is 9, -2 is 4, positive 2 is 4, positive 3 is 9. And I have a set of the original numbers, -3, -2, and so forth and so on. D is a dictionary, S is a set. Here I have an empty dictionary, and here I have an empty set. Both the set and the dictionary use the same curly braces to indicate this is a collection of some elements. The dictionary has a colon, and the way you disambiguate is this a set or a dictionary? Is the dictionary is combining two data sets. It's got a colon for the left-hand side, the key, and the right-hand side, the value. The set doesn't. But if this were an empty structure, well, is this an empty dictionary, an empty set? Dictionaries came first in Python. This is an empty dictionary. A common mistake that people make is they write S equals this, empty set, and they even put a comment there. Empty set, this is not an empty set, this is an empty dictionary. Some people have suggested maybe we should have something that looks like this for an empty dictionary and this for an empty set, but that would require breaking backwards compatibility with a lot of old code. And so be very careful when you create an empty set. You want to write it like this, or if you're very ambitious, you could write it like this. But unfortunately, we won't be able to talk about what this unpacking syntax really does, but both of these are empty sets. What do we do with all of this information? What do we do about this? When you're working with one data set, consider using a set if the elements are unique and you're okay with it silently eliding duplicates, and if the order of the elements doesn't matter, you don't care what order they show up in. When working with two data sets, consider using a set if you care about operations, set-like mathematical operations. What are the elements in common? What are the distinct elements? What are the total unique elements? It is a common thing that shows up in my work. It is a very useful tool. It's in the built-ins, and it's something that I would encourage you to use because it may not lead, the failure to use a set may not lead to buggy code or broken code, but it'll lead to suboptimal code, code that is harder to read or that hides bugs. Our goal here is not only to spot bugs, but to figure out how to avoid bugs by using better tools, better structures, and better approaches. If you liked this session, I've got good news for you. We have another session tomorrow. And tomorrow's session is Spot the Bug, Pandas, and NumPy edition. We will be going through another batch of questions, and in those batches of questions, we'll show you a bunch of things that show up when you're writing your Pandas and NumPy code. In the case of Pandas, create error messages that just scroll on and on and on and on, and you can't even figure out, wait, which line had the error in the first place? What on earth does it mean? Setting with copy warning. Oh my goodness. We will be going over those, giving you an opportunity to spot the bug, giving you an opportunity to win yet another prize or set of prizes. That's what we have in store for you tomorrow. Spot the Bug, Pandas Edition. If you have any questions that you didn't get answered in the Blue Jeans chat, please do reach out to us by email or on Twitter, and we'd be more than happy to answer that. And if you liked this session, we'd love to know. But I think that takes us to the end of the bugs that we've written. I wrote a lot of buggy code today, but I hope that buggy code was not frustrating, but illuminating. I hope it gave you an opportunity to think a little bit more about the basics of Python so that when you're writing even very simple Python code in your day-to-day work, maybe even using Python for the first time, you can spot the bugs and think about what those bugs mean, avoid those bugs, and figure out how to be a better programmer. With that said, thank you all for joining us. This has been Spot the Bug. I'm James Powell, and hopefully I'll see you for a future session.